When you picture outer space, it is incredibly tempting to just imagine this vast, silent, empty void.
Right, just total quiet.
Exactly.
Yeah.
But if you were to actually, point ground-based radio telescopes and space observatories toward the very heart of our own galaxy, the Milky Way, you would find this chaotic symphony.
It's so loud.
Yeah. For decades now, astronomers have been picking up these bizarre, incredibly energetic gamma-ray signals coming from the galactic center. It's essentially this cosmic noise that just does not fit the standard models of astrophysics.
No, it really doesn't fit at all.
So today's deep dive pulls from a new theoretical model by researchers at King's College London. It was recently published in the Astrophysical Journal Letters, and it was highlighted in a great Patreon article we're using as our main source today. This team thinks they might finally have the key to decoding this noise.
It really is one of the most persistent, frustrating mysteries in modern astronomy.
Frustrating is a good word for it.
Yeah, and to understand the gravity of what this King's College team is proposing, we have to establish the baseline of the crime scene for you.
Set the stage for us.
Right. So the center of the Milky Way is not some quiet stellar neighborhood. The galactic nucleus is an extreme environment. It's densely packed with staggering amounts of mass, swirling interstellar gas clouds, and just violent, highly energetic phenomena that are constantly reshaping the region.
Okay, let's unpack this.
Yeah.
If you are trying to visualize the baseline noise floor of this region, imagine the galactic center as the most chaotic, overcrowded, metropolitan downtown you can possibly think of.
It's like New York or Tokyo during rush hour.
Exactly. It is a perpetual rush hour. There's heavy construction on every block, and sirens are blaring everywhere. You expect a high baseline of noise.
You do.
But within all that expected chaos, astronomers keep isolating 3 very specific rogue notes that are completely out of tune with the rest of the city's machinery.
Yeah, and to figure out what is broadcasting those rogue notes, the initial instinct of the astronomical community was to look at the loudest, most obvious engine in the room.
Which would be Sagittarius A*.
Exactly. The supermassive black hole anchoring the center of our galaxy. It has this immense gravitational power to accelerate particles to near light speed.
And that easily generates gamma radiation.
It does. But the source material highlights a crucial turning point in this investigation. Researchers maintain that these specific emissions are definitively not coming from Sagittarius A*.
See, if you're a detective, that is a wild twist.
It really is.
The biggest, most destructive monster in the room is completely innocent of this specific phenomenon. How do they know that for sure?
Well, the spatial distribution of the radiation gives a black hole an alibi.
An alibi, I love that.
Yeah, because black hole emissions, especially the high-energy flares from an accretion disk or those massive relativistic jets, they tend to be highly localized and variable.
Meaning they pulse and change over time.
Right. But the gamma-ray signals we are talking about are diffuse. They are spread out across a vast region of the galactic bulge, and they are steady.
So it's more like a blanket of radiation rather than a spotlight.
Precisely. And because we can confidently rule out the central black hole, and because conventional astrophysical processes...
Like pulsars or supernova remnants.
Right, because those fail to match the specific energy signatures, the investigation is really forced to look for a non-conventional mechanism.
So if standard stellar physics and the supermassive black hole can't account for the noise, we need to look closely at the actual profile of these 3 rogue notes.
Let's lay them out.
The source lays out 3 specific anomalies, all occurring in what they call the low-energy regime of gamma radiation. Clue number 1 is the 511 keV emission line.
Which is a very sharp, highly specific frequency of energy.
Right. Clue number 2 is a gamma-ray continuum peaking around 2 MeV. And unlike that first sharp note, this is a broad, continuous spectrum of energy.
Like a lingering hum, rather than a single bell ringing.
Yeah. Exactly, a hum. And then clue number 3 isn't actually a direct energy signal hitting our telescope lenses, but an environmental effect.
Right, it's intense, highly unusual gas ionization behavior.
Localized in a region known as the central molecular zone. The gas there is being stripped of electrons, as if it's being heavily bombarded by something.
And historically, the scientific paradigm treated these 3 anomalies as entirely independent phenomena.
They just thought they were unrelated.
Yeah. Astronomers documented the sharp 511 Keavy line, the broad 2 MeV continuum, and the ionization, but assumed there was no common physical origin linking them all together.
See, I have to push back on that historical disconnect.
Oh, yeah.
Yeah. If these three completely bizarre anomalies are all happening in the exact same region.
The extreme, crowded downtown.
Right, that extreme downtown of the galactic center, it feels counterintuitive to assume they are unconnected.
Were they just so structurally different that tying them together seemed impossible at the time? Well, it really comes down to the underlying quantum mechanics required to produce those different signals.
Yeah.
Superficial proximity isn't enough to link them because the physics generating them seemed irreconcilable.
How so?
Well, a sharp emission line, like the 511 Keavy signal, implies particles interacting at rest. That produces a highly specific, clean quantum energy jump.
At rest. Got it.
But a continuum, on the other hand, implies particles colliding at relativistic speeds.
Moving super fast.
Right, where excess kinetic energy smears the resulting radiation across a broad spectrum. So finding a single mechanism that simultaneously produces massive amounts of particles at rest and massive amounts of particles moving at near light speed.
While also ionizing the surrounding gas clouds.
Exactly. Finding one cause for all of that was incredibly difficult.
It's like finding a shattered window, a burned-out car, and a flooded basement on the exact same city block.
That's a great way to look at it.
It is just statistically easier to assume a rock, a fire, and a busted water main happened independently, rather than trying to invent one single, incredibly complex event that perfectly caused all three.
And that is the revolutionary aspect of this King's College London study. They stopped looking for the rock, the fire, and the busted pipe.
They looked for this single event.
Right. They realized that conventional baryonic matter, the normal protons and neutrons that make up stars, gas, and black holes.
The stuff we can see.
Yeah, that stuff could not provide that single unifying event. So to find the common thread, they shifted their focus entirely to the dark sector.
Which brings us to dark matter.
Yes.
But the researchers aren't just blaming standard dark matter models here. They're pointing the finger at a very specific theoretical framework called excited dark matter.
And to understand how excited dark matter operates, we first have to look at its kinematics at the galactic center.
Okay, lay it on us.
The density of the dark matter halo increases dramatically as you move toward the core of the Milky Way. The particles are packed incredibly tightly, and the intense gravitational well means they possess a much higher velocity dispersion.
Meaning they're moving much faster than dark matter particles out here in the galactic suburbs.
Exactly.
So higher density and higher speeds mean a drastically increased probability of these dark matter particles colliding with one another.
Well, normally, under standard models, dark matter is collisionless.
Right, it just passes through stuff.
Yeah, it passes right through itself, and regular matter like a ghost. It's completely dormant in its lowest energy state, interacting only through gravity.
But this new model changes that.
It does. The King's College model introduces a mathematical catalyst. They hypothesize that in this hyperdense, high-velocity environment, dark matter particles actually can and do collide.
Because of a fifth fundamental force.
Yes, driven by a fifth fundamental force.
Okay, wait, hold on. A fifth fundamental force.
I know, it sounds massive.
Are we just inventing entirely new rules of physics to explain why these invisible particles are colliding? I mean, we have gravity, electromagnetism, and the strong and weak nuclear forces governing everything we know.
It is a natural reaction to view introducing a new force as an overreach.
It feels like forcing the math to work.
Sure, but this is deeply rooted in the history of particle physics. I mean, think about it. We didn't know the weak nuclear force existed until we observed radioactive beta decay.
And realized the standard equations were missing something.
Exactly, they were missing a fundamental mediator. If the universe contains 5 times more dark matter than regular matter, it is mathematically plausible, if not probable, that the dark sector possesses its own internal dynamics.
Okay, so just as electrons interact via the electromagnetic force by exchanging photons.
These researchers are modeling a scenario where dark matter particles interact by exchanging a dark force mediator, a fifth force that only operates outside our standard model.
Wow. Okay, so under this dark gauge theory, this hidden force allows these fast-moving particles to physically crash into each other.
Yes.
What is the actual mechanism that follows the collision?
When they collide, they exchange kinetic energy. Some of these dark matter particles absorb the energy of the crash and are forced into a higher mass state.
And that is the excited phase of the model.
Exactly. But much like an electron that has been pushed into a higher orbital, that excited state is unstable.
It wants to drop back down.
Right. The particle cannot maintain that extra mass energy forever. It rapidly decays back down to its dormant, lowest energy state. And the conservation of mass and energy dictates that the excess energy has to go somewhere.
And according to the study, that decay process bleeds off the excess energy by spontaneously creating matter and antimatter pairs out of the dark sector.
Which is mind-blowing.
It really is. Specifically, it produces electrons, which are regular matter, and positrons, which are their antimatter equivalents.
And the spontaneous generation of those electron-positron pairs is the engine that drives the rest of the theory.
Because it resolves the anomalies.
It elegantly resolves all three of our historical anomalies. Let's look at the first clue, the sharp 511 keV emission line.
The clean bell ring.
Right. When a newly created positron is ejected into the galactic center, it eventually encounters an electron. Now, when matter and antimatter meet, they annihilate. Boom! But the kinetic energy of the positron dictates how that annihilation happens. If the positron has time to shed its initial speed...
If it slows down and thermalizes in the interstellar gas.
Exactly. If it does that, it approaches the electron at a low velocity.
So they don't just instantly explode, they get caught in each other's electromagnetic pull.
They enter a mutually bound orbit. They form a temporary, highly unstable hydrogen-like atom known as positronium.
Positronium.
Yeah, it is a fleeting death dance between matter and antimatter.
That's poetic.
It is. And when that positronium structure inevitably collapses in on itself and the two particles annihilate, all of their rest mass is converted purely into energy.
And because we know the rest mass of an electron is exactly 511 kilo-electron volts, Einstein's E equals mc squared guarantees that the resulting photons shooting out from that annihilation will carry an exact energy of 511 keV.
The math is beautifully rigid.
That completely explains the first anomaly, the sharp rogue note astronomers have been measuring.
It accounts for the diffuse, steady hum of that specific frequency perfectly.
Wow.
But the King's College team didn't stop there. They applied the kinematics of the dark matter collisions to the second anomaly.
The 2 MeV gamma ray continuum.
Right. Remember, the decay of excited dark matter ejects these positrons with high initial velocity.
They come out hot.
Exactly. So what happens if a positron encounters an electron before it has a chance to slow down?
Oh, if it hasn't thermalized, it still carries a massive amount of kinetic energy, so they don't have the chance to ease into that bound positronium orbit.
Exactly the opposite. They undergo what is known as in-flight annihilation.
The fast-moving positron violently smashes into the electron.
Yes. And in this scenario, the resulting photons don't just carry the 511 keV rest mass energy. They also carry all of that excess kinetic energy from the high-speed impact.
And because the collision speeds vary, the resulting photon energies vary.
Right, which creates a smeared, continuous spectrum of gamma radiation that peaks in the megaelectron volt range.
Which perfectly maps to the 2 MeV continuum.
Exactly.
And that brings us to the third anomaly, the intense gas ionization in the central molecular zone.
The smoking gun for the environment.
Right. If you have a massive population of hyperfast antimatter positrons being continuously generated by decaying dark matter, and they are tearing through the galactic center before they annihilate, they're going to physically strip electrons away from the ambient gas clouds just through sheer electromagnetic interference.
The kinetic transfer of energy from the relativistic positrons passing through the molecular zone provides the exact ionization rate required to match the anomalous telescopic observations.
The mechanism here is so elegantly layered. Here's where it gets really interesting for you, the listener.
Yeah, let's tie it together.
If you are listening and trying to visualize how one cause creates these three vastly different effects, think about the initial dark matter collision as two cars crashing on a highway.
Okay, I like this.
The decay of the dark matter creates our matter-antimatter pairs, basically the flying debris of the crash.
Right.
Now, if two pieces of debris just lightly scrape against each other at low speeds, the metal makes a very specific, sharp ping.
Which is the positronium forming and cleanly decaying into the 511 key photon.
Exactly. But if two pieces of debris hit head-on at much higher speeds, it doesn't make a clean ping. The kinetic energy generates a massive, loud boom.
That in-flight annihilation is our broad 2 MeV continuum.
Right. And while all this is happening, the sheer volume of debris flying through the neighborhood is smashing into parked cars and setting off alarms down the entire street.
That is the ionization of the gas clouds. The physical parameters of the decay process dictate the observable outcome. Depending on the velocity of the positron at the exact moment of interaction, the excited dark matter model effortlessly produces the sharp line, the broad continuum, and the environmental ionization. Simultaneously from a single root cause.
Seeing those three distinct threads pull together fundamentally changes how we view the galactic core. It is really worth highlighting the perspective of the researchers themselves on why this unification matters.
Definitely.
The source material features a quote from the study's co-author, Shyam Balaji, a researcher from King's College London. He states, and I quote, "There are three different seemingly unconnected signals, but the point we're making is that a specific model of dark matter can explain at least two of them and potentially contribute significantly to the third."
If we connect this to the bigger picture, Balaji's point strikes at the core of theoretical astrophysics.
How so?
Well, the ultimate goal of the discipline is to reduce the apparent chaos of the universe into elegant, predictable laws.
Right, simplifying the complex.
Yeah. For decades, the paradigm required overlapping, completely disconnected theories to explain the center of the Milky Way. Replacing those disparate theories with a single, cohesive quantum mechanism is a massive leap forward in our understanding of galactic dynamics.
We do have to maintain absolute impartiality here, though. We need to present the major reality check that the authors heavily emphasize in the text.
Very true.
As perfectly as the math aligns with our telescope data, dark matter itself is entirely hypothetical.
Yes.
It has never been directly detected in a laboratory or by a sensor.
It is a critical caveat. The entire model of excited dark matter driven by a fifth fundamental force is a mathematical framework.
It's math on paper.
Right. It
Yeah.
is designed to perfectly fit the observational constraints of the crime scene, but a mathematical fit does not automatically equal proven physical reality.
Exactly.
Until we can isolate a dark matter particle, this remains a highly compelling, beautifully structured hypothesis.
So what does this all mean for you, the listener? Why should we care about a hypothetical solution to an invisible problem? I mean, it comes down to predictive power, right?
Absolutely.
This model takes dark matter from being this frustrating abstract concept, just missing mass that bends light, and turns it into something that produces highly specific, traceable exhaust fumes.
It provides the astronomical community with a definitive roadmap. We are no longer blindly staring at the galactic center, wondering what is generating the noise.
We know what to tune into.
Exactly. If the King's College London model is an accurate representation of reality, we know the exact mass states to calculate and the precise decay rates to look for. We have a testable spectroscopic signature.
But to actually prove this framework, we have to look to the immediate future of space exploration.
We do.
The current generation of ground-based and orbital telescopes gave us the initial baseline clues. But to confirm a mechanism this complex, we need next-generation tools.
The confirmation completely relies on future MEVI gamma ray observatories.
Like better sensors in space.
Right. We need instruments capable of analyzing the central molecular zone and the galactic bulge with unprecedented pinpoint spatial resolution.
Wow.
If a future observatory can map the exact distribution of the 511 KeV line and the 2 MEVI continuum and prove that their intensities perfectly correlate with the predicted density map of the dark matter halo,
That would be it.
it would provide the smoking gun. It would confirm that we are observing the direct decay products of the dark sector.
It is incredible to consider that the answer to one of the most profound mysteries in particle physics might be hiding in plain sight.
Just disguised as background noise in the busiest part of our galaxy.
Exactly. We started this deep dive talking about how easy it is to view the universe as a silent void. But the center of the Milky Way has been broadcasting the mechanics of dark matter at us for decades. We've been waiting for someone to figure out the translation.
It shifts our entire perspective on what constitutes the universe. We are forced to acknowledge that the visible matter we interact with might just be a minor byproduct of a much larger invisible framework.
And that leads to a truly staggering implication to think about.
Oh, yeah.
Yeah. If the dark sector isn't just an inert, heavy anchor holding galaxies together.
Right. If it's not just dead weight.
Exactly.
Yeah.
If it actually possesses its own distinct fifth force, its own complex gauge theories, and its own excited quantum states that can spontaneously generate antimatter, where does that complexity end?
That's a huge question.
Could there be dark chemistry?
Wow.
Could these internal dark forces allow invisible particles to bind together, forming dark stars or entire shadow galaxies operating parallel to our own?
It's completely possible under this framework.
We might be sharing the exact same space with an entirely hidden universe of complex structures, completely oblivious to each other simply because we don't share the same fundamental forces.
That is wild to think about.
Something to think about the next time you look up at the night sky.
Okay.
Thanks for joining us on this deep dive.
Ah.
Keep questioning the noise.